Hello everyone. So far we have considered functional of curves given by equation of the form y is equals to y of x in two-dimensional case. However, sometimes it is more convenient to work with parametric equation of curves. Moreover, in problem involving closed curve like isoperimetric problems, it is usually impossible to get along without representing the curves in parametric form. Thus, in this video, we extend our previous result to case where curves are given by the parametric form. So let's get to our board and let's write our functional. So our functional j is equals to the integration from x1 to x2, or let me use the another symbol for the limit. The convention should be x0 to x1, and the function f which depend on x, y and y prime, and then a dx. In parametric form, however, it is represented by the following. So in the parametric form we will write it as the integral. We are using the parameter t here, and the limit for t is from t0 to t1. F x in term of t, so this is x of t, and then y in term of t, so y of t, and then we have a y prime, so we write it as y of t dot divided by x dot of t, and on the outside we have a dx which is written as x dot of t into dt, where x dot is represent the time derivative of x, or basically we are not concerning with the time but just the t derivative of x, and y dot represent the t derivative of y. So further we can write it as limit from t0 to t1, writing it as another function which I calling phi depend on x, y, x dot and y dot. This functional depending on two unknown function x of t and y of t, and phi does not involve t explicitly, and is positive homogeneous of degree 1 in x dot and y dot, and that is clear from the form of capital F, because we have a dependence on y dot and x dot as a fraction, so we have I dot upon x dot, and from the definition of homogeneity we can say that this is a homogeneous in x dot and y dot with the degree n, is equals to 1, or in another way we can write it as phi x comma y lambda x dot comma lambda y dot, and that is equivalent to lambda times phi of x comma y x dot and then at y dot. So we have a lambda to the power 1 because this is a first order homogeneous equation. Now we will show that the functional depend only on curve in xy plane defined by x is equals to x of t and y is equals to y of t, and not on a function x of t comma y of t themselves. And what I mean by this is that if we go from t to some another parameter, let us suppose tau. So if I go from t to some another parameter tau by the transformation t of tau is equals to t, then the interval will also be changed. So interval, let us suppose interval change from t0 t1 to tau naught comma tau 1. So how the functional will be changed? So functional will be limit from tau 1 to tau 2, then phi we have a x y, and then we have to write x dot in term of tau. So we write it as dx over d tau comma dy over d tau into d tau is equals to t1 into t2 phi x y x dot y dot dt. So what we get is that the functional does not depend on the x of t and y of t, but it just depend on the curve in xy plane. So we have to prove this argument, which I write it here, and how we are going to do in the following way. So in fact, the integration, the limit tau 1 to tau 2 phi x comma y dx over d tau dy over d tau. So this looking horrible. Let me change this from dy d tau. What next we will do is to write this integration as x and y will be same as before, and here we will multiply with dt on a both hand side. So what we get is that we get a x dot from dx over dt, and then a dt divided by d tau. Again we do the same trick and we get the following. And because phi is homogeneous of order 1 in x dot and y dot, we get the this factor out of this integration. So what we get are dt over d tau outside. So let's get this dt over d tau outside the bracket. So what we get a dt over d tau and the d tau. So d tau and d tau will be cancel out, and what we get is a dt. So you can see the limit will be also same because the integration is now with respect to t. So limit goes from t0 to t1. So this proves the following argument what we made earlier. Thus we have proved the following, and again recall that integration from t0 to t1 f of x comma y x dot divided by y dot x dot dt is equals to integration from t0 to t1, and then this is phi x comma y comma x dot and a y dot and the dt. So this is actually a y dot. So the variational problem for right hand side lead to the pair of Euler equation, because we have x dot and y dot, we have x of t and y of t. So as in previous video we see that if you have more than variable you get a system of Euler equation. So let us write the system of Euler equation, which is phi of x minus d over dt pi x dot is equals to 0, and the second equation will be in y is equals to 0, which must be equation equivalent to the functional on a left hand side, because these are equivalent to each other. And for the f, we have a functional which follow the Euler equation given by f sub y d over dx f y prime is equals to 0. Hence, the Euler equation, the system of Euler equation cannot be independent. This system of equation cannot be independent, and thus in fact you can verify that they are connected with the following equation in f. And you can in fact show as an exercise that the following equation is true, that x dot pi x minus d over dt pi x dot plus y dot pi y d over dt pi y dot is equals to 0. So this I am leaving for you to verify that these system of Euler are actually connected to each other, not are independent. And we shall do a further discussion on this point as we go along. So that's all for this lesson. See you in the next lesson.